Right, Marcel. So thanks so much for your question. This is a different one. I can definitely help you with this. I'm sorry that it's taken me a little bit to get back to you. I've just been away for a bit, but hopefully this is your assignment. I can still help you out. Um, so I guess to start, there's data here, right? And if we just look, I just kind of like listing what do I actually have. I've got an angle, I've got time, I've got velocity, I've got acceleration, and I've got a force. Um, what this suggests to me is particularly, and what gives it away, I think, without any other context, is this idea that there's a component down that's mg sine theta. What that tells me is that we're looking at some kind of inclined plane scenario here, where we maybe have some kind of block at the top up here. We've got an angle of elevation that's changing. And then we've got, as the block slides down the plane, there's a time that it takes to slide down the plane. There's an acceleration, and there's obviously a velocity, and a force. And so we can find all these. And so the relationship here is, okay, you're going to have a velocity and a time. From that, you can get acceleration. From that, if we know the mass, we can find force through F equals ma. And so that's my assumption here with what's going on in your question. I'm not sure if this is from your assignment or it's just a scenario that you've been given, but that's my understanding of it. If that's not correct, I'd love for you to let me know in the comments, because it might affect the answer a little bit, but that's my assumption, right? And so if we wanted to determine the relationship between angle and time using data, this is kind of the key. And in physics, it's very literal a lot of the time. And so when it says to use data, I'm literally going to say, okay, and angle, we're just taking pure angle, pure time. Our angles go from 5, 10, 15, 20, 25. Our times then go down a different color. Our times then just go 1.53, 1.08, 0.89, 0.77, 0.69. And yeah, so I guess what the instinct is here, if you're just describing a trend, the very first thing is that as angle increases, time decreases. And it seems like self-explanatory and not really like too much of a conclusion to make, but that's actually what they want you to write, even though it's really simple. So there's that, and then it's also, okay, yes, we know that happens, but by how much, to what extent? And something you can look at, you can just eyeball it, and you can see, okay, well, the angle is consistent, it's +5. The time's not. It's a bigger jump here than it is here, and that jump gets smaller. And I don't think it's going to be, well, I can tell you what it will be. It'll be a sinusoidal relationship. But here we can say that, look, maybe if we think about graphing it, right, like just a sketch, like I'm not saying actual graph it, but we've got 5, 10, 15, 20, 25. Our time kind of is going like this, right? Or maybe more. So something you can talk about here is you could either divide the two and see, okay, like what's the difference between them? Because sometimes you'll find, okay, as one doubles, the other halves. That's not really what's happening here. I think it's more of this sinusoidal, parabolic, or even like logarithmic looking relationship. So I would say that in words, as the angle increases, time decreases. However, these decreases become smaller as the angle gets closer to 25. This might reflect a sinusoidal relationship, something in those terms. But I know you wanted more help with these bottom ones, so I won't dwell too much on that. The mathematical, this is slightly different. So we've got, this is a relationship. This is now the mathematical relationship. So this is different. And what this implies to me, if we look at what we've got, it's talking about acceleration and sine of the angle. The angle here is our independent variable. That's what we're changing. And it's kind of like difficult maybe to know what, okay, the dependent variable is here. It's acceleration. What gives that away is that you've got theoretical and observed. You're not going to have your theoretical values unless you've got something to compare them with. And so I'm going to suggest that sine of the angle is our independent variable. Acceleration is our dependent variable. Therefore, we can come up to our actual equation for the graph. And again, I have no context here, so this might be wrong. But I'm going to assume that your graph measures acceleration as the y component and measures sine of theta as the x component. In which case, the mathematical relationship would be that acceleration equals 9.9969 sine of theta minus 0.012. That would be how I interpret the question without any other contextual information. Okay, draw a conclusion of acceleration and sine angle. Include the meaning of gradient. Justify your answer. Okay, so this is interesting. There's a few things here. So this type of equation, where you've got y equals mx plus c, that represents, okay, we've just got a linear relationship. A linear relationship that starts below the axis because we've got a negative c value just a little bit, like it's basically 0. And then it's got a consistent trend. It's almost 10 as well. So the conclusion that I would draw, and gradient here, it suggests, okay, well, when we go up by 1 sine of theta here on the side, so, and it won't be 1 and 2, but we'll just say like 0.5. Acceleration will jump by from 0 to 1. It can go from 0 up to 10, basically. And so if I'm talking about, okay, I need to draw a conclusion about that and include the meaning of gradient. The gradient here is, or the entire relationship is linear. And it suggests that the gradient, first of all, we can identify as 9.9969, which is approximately 10. And that shows that the relationship between acceleration over sine theta is roughly 10. And so whatever sine of theta equals, acceleration is roughly 10 times that. Yeah. That's like, we've got, you could also, if we're thinking about this in terms of a data test kind of question, you've also got this idea of proportionality. So acceleration is directly proportional to sine of theta in some way here. We've then got this idea that therefore acceleration equals some constant k times sine theta. The gradient is our constant. So it shows like to what extent it's proportional. So k here is about 10. Okay. Predict the angle when acceleration is 5 meters per second squared. So obviously there is no 5 So what we can do is come to our equation and say, okay, if this line was to continue, what should the angle be? We can do that. So we're going to take our formula, and we want a to equal 5. We've then got everything else that we had before. Sine, that's a 9, sorry. Sine of theta minus 0.0192. And so now I've just got one unknown, and this is just going to be calculator work. So I'm going to start by moving our decimal there to the other side. So that's going to become 5 plus 0.0192. So that gets us 5.0192 on this side. We've got the same over here. Now I want to free up this sine theta. So I'm going to divide both sides by this number here. So I'm going to take my 5 point something or other, divide it by, and that'll get me 0.502, just about, equals sine theta. So then to solve for theta, that's the inverse sine of that value. Which will give us inverse sine of answer about 30 degrees. So the angle is approximately 30.14 degrees here. And if we just want to verify that logically, that makes sense because our acceleration increases as the angle increases here. We stop at 25 and we stop at 4. It does kind of follow that if we increase it to 30, it would be somewhere in the range of 5. So we can say it's a reasonable solution. And then finally, and I'm guessing this is the part that you maybe wanted help with, is absolute percentage error. I'll direct you to a formula on the formula sheet that will help us out with this. Okay, so a lot of people actually overlook that things like this are on the formula sheet, but it's helpful. Like instead of if you are kind of lost and you don't know how to do it, it is always just worth checking. Like there's a lot of things on the formula sheet that are there that you might not expect, so you don't actually need to remember. So let's calculate the percentage error first, and then from that, let's calculate the absolute error. And what are we looking at here? Well, it comes back to this idea of observed versus theoretical. That's the giveaway. And if you look at the formula, observed is going to be our measured value, and our true value is going to be the theoretical. So if we plug that in, and here we would have an individual error for each calculation. And it's not super clear like whether they want us to do it for every single calculation, but it's assumed. Like if you're making a graph, you kind of want your error bars to be at each of the points. So yeah, let's work off what we got. What we have is acceleration observed, acceleration theoretical for each point. And so we can do it. I'll just put bracket for like which point it is. So for the first one, I can already tell you it's going to be 0 because these two are the exact same. So if we subtract them, it's just going to be 0. So our error for the first one is plus or minus 0 or just 0. There is no error. Great. Percentage error for the second one. We're going to actually have a value here. So and this means absolute value. So if it's a negative, we just take the positive. So measured value was 1.71. Then our true value is 1.70. We're dividing that by 1.70. Absolute value times 100. That will give me 0.59%. So pretty small there. And often error, they just want it to one decimal place, so that's 0.6 in that case, if that's what they're looking for. All right, this one's going to be a little bit bigger, I think, with the 3. So here we've got some. 2.52, and then the theoretical is 2.54. So 2.52 minus 2.54 over 2.54. And here's where the absolute value is important, because you can see here, if you subtract a bigger number from a small number, it'll be a negative. I'm just going to stuff up our calcs. So that's where the absolute value comes in, and I will put that in my calculator. Okay, so that I get 0.79%. So still really small. It's approximately 0.8%. Beautiful. Then 2 more to go. We've got 3.37 and 3.35. So 3.37 minus 3.35. I'll just double check that. Yep. Over 3.35 times 100. This will give us a percentage. 3.37 divided by 3.35. Oh, no, sorry. Subtract first. And divide by 5 times 100. Again, that's a smaller, that's 0.597%, but essentially 0.6%. And then, yeah, I think we get the idea. We can repeat it for that last one as well, which I'll do right now. Okay, so that last one got me 1.4, which is a little bit higher. But yeah, that's percentage error done. Now we've got to calculate the absolute, and this is pretty simple. We just take the actual percentage and figure out, okay, what does that, how much does that equate to relative to the actual value? So the first one, 0 is still just 0. But for the second one, and this is, sorry, we're applying this to the value that we observed. So we're going to take these values over on the left. So this one, this one, this one, and this one. I'll just double check that they're right. Yep. Okay. And so when we come over here to calculate our absolute, the rounding might be a little bit off here. I haven't stored it in my calculator, so I'm just going to use these rounded to 1 decimal place values. Might differ very slightly. Okay, so essentially all I'm going to do is say what is 0.6% of 1.71. You can either do this with the percentage button, or you can just convert this to a decimal, so back to decimal places. Similarly here, we're going to go 0.8% times 2.25. Here it's 0.6% times 3.37. And finally, 1.4% times 4.20. So I'll just do that in my calculator now. And then, yeah, we'll have our final answer. All right, so we go. These are all the errors that I got. Absolute errors rounded to 2 decimal places. Note that I've actually included the units here because it's a unit of acceleration. And yeah, that's what I do for all those questions there, Giselle. I'm sorry if I got anything wrong here. I apologize if I've missed some context. It's important, or maybe something that your teacher wants to do specifically. But I hope that's helpful, and it's a good overview of just how to analyze data generally. Specifically if it's relating to a student experiment or something like that, and calculating error, which I completely agree can be confusing at first, and also error versus uncertainty. If you get stuck, it's here. It's on the bottom sheet. So you can always come back to that. But yeah, I hope that was really helpful. And if you learned something from this, I'd really appreciate if you could like the video. Go support us on YouTube and our other socials as well. But yeah, it's a pleasure. Thanks so much.